Kajasoke from CPUT, mechanical, actually industrial mechanical engineer, but at CPUT I teach mechanical engineering design and thermodynamics. I want to talk to you about spreadsheets in mechanical engineering design. I don't know how many.
Sorry to interrupt you. If you want to record it, you have to be on the other side. Yeah.
I want to talk to you about mechanical engineering design. I don't know how many of us are mechanical engineers here. Okay, excellent. It's about the course I'm taking. I want to show you how I handle it. We'll see some quite interesting results, I hope. In the highlights, I'll give you an introduction on mechanical engineering design. I'll show you how I calculated it to match what I think it should be. I'll show you some spreadsheets, how I used spreadsheets to help the students learn. I'll report on the students' feedback, and finally we'll see what I call dreams coming true. Dreams coming true. Okay, let's see. Mechanical engineering design basically deals with dreams. Okay, human needs. Okay, served by mechanical engineering systems. That's the main thing. It involves application of the physical sciences, which normally in engineering education we call engineering sciences, to serve human needs. Without human needs, no need for design. And it integrates all areas, okay? All areas of knowledge, humanities, geography, science, I don't know what, all those, they have to be integrated. In actual fact, ladies and gentlemen, the arts are the king. Normally in engineering education, we think that the physical sciences are the king and maths is queen. This is not true. The humanities are the king, maths is our queen. The physical sciences, if you are looking at the chessboard, they are simply a pair of rooks. And I'll show you shortly what I mean by this. I just give you two examples on just traveling. Somebody there has a problem. This is typical in Africa, north of the Congo. There's a small parasite there, and this fellow here, you can see his feet. That parasite has attacked his feet. This fellow here has a dream. The owner of that foot has a dream. He wants to be able to walk from his house at least to the outside to enjoy a bit of the sunshine. That is his dream. So the problem causes a dream. The solution really is to have a safety pin, remove this guy from those feet there, and it's mechanical engineering design which does that. On the other hand, you have another problem here, second problem. We are now talking of interstellar travel. We want to move to the next star. This is Max Planck Institute. So this is Earth, and we are talking of going there. We can go there at 20%. It has been envisaged that we can go there at 20% the speed of light. The issue then is how to brake. When you reach there, okay, the Centauri star system, How do you break from 20% the speed of light so that you can capture whatever you have to capture? So there is a dream there also. There is a dream there. And using gravitational forces, okay, it has been worked out that that is possible. So there is a dream. Problem of breaking, this is the dream. Both of these problems are involved traveling and the knowledge that we need to use is physical sciences, maths, and other knowledge, and also plus a bit of math. Mechanical engineering is like, it's not just sciences, it's not just arts, there is also a bit of math. But this is the driver. So what are the issues that I find in engineering education at university? There are several. I have found that universities treat engineering design as simply an extension of engineering sciences, which it is not. Which it is not. Then, most importantly, the arts, the humanities are almost completely ignored. In which case, there is no king on a chessboard. In which case, the students are presented with no king on a chessboard. And most interestingly, the mathematical modeling is very, very rudimentary. It's very, very rudimentary. It's unrealistic. And for the university sorry about this, colleagues, for the university I work with, there was a problem. The second design option was optional. As a result of that, students, I can say, were living, for lack of another word, half-baked. So what was my problem? My problem was to motivate students to treat it as an integrative subject, okay? And get them to construct real working machines right at the university. The other objective was this business of the second design module being an option has to be banished from the students' minds. Methods. I'll show you methods in these 2 areas. How I address the issues and how I measured the effectiveness. In the issues, the curriculum was informally redesigned. That is on own initiative. Secondly, engineering design was reintroduced to the students as a new body of knowledge, not just an extension of engineering science. Spreadsheets were used, okay, as we shall see. And then on the testing side, I find key performance indicators for myself and the students. And I had multi-control samples, as we shall see, and I used Lingard scaling in the analysis. Let's quickly go through them one by one. Informal design, curriculum redesign. Conventionally, this is what we have, and this is the new. I introduced engineering, humanities in engineering science applications. Then I treated the, normally here, the machine elements are treated independently, but there we treat them, now we treat them as interdependent, serving arts and maths, using maths. Then we normally, in the normal curriculum, we move from elements to assembly design. But here, we start with the arts, the humanities, the need, then we go to the assembly of the elements, and then look at the elements themselves. Then, normally, design tends to focus on novelty, engineering novelty. Our focus right now is on social and economic sense. The students are inculcated to think about social and economic sense. Then, Normally, it is treated qualitatively and quantitatively at the same time. But right now, we first deal with the quality of the elements, then move to the quantitative treatment in a multi-constrained arts environment. In other words, for example, look at economics, look at safety, look at environment protection when we are designing our. Then finally, normally, this produces an engineering design, engineering drawings as the final outputs. I say no. We have to have working machines as the final output. As a new body of knowledge, let's see, we deviate. Okay? From normal engineering science, okay? I emphasize good engineering practice principles. We apply engineering design codes. We use standard machine elements, and we show the students how to use manufacturer catalogs. And then we design for X. Designing for X means designing for a particular purpose, designing for maintenance, designing for manufacture, designing for marketability. And so we look at those things. Spreadsheets. Okay. Oh my God. Spreadsheets. There we are, and I have one here. The spreadsheet basically, I designed these spreadsheets to help the students do that. The main thing is that the student concentrates on things there, and then the calculations are done automatically. Testing effectiveness, I have key performance indicators, which I will just show you. There are 3 of them: teaching and learning, arousing, innovations, and let's go to, I'll quickly go to the results now, I think that's the most important thing. There are 3 results on those key performance indicators. That's the feedback on teaching and learning. Students were able to learn better. Overall, on 10 units. And this is an analysis of wishing students wanting to come back with that course. Initially, less than 40% wanted to do the second design, but now after the third design, they want even more. I want to show this. I hope we remember that.
Yo.
The students designed a fluid emulsifier and heating cooling system. There it is. There they are. And if I can run a 30, that's the unit running. Incidentally, in 2001, I designed something similar to that for my own factory back in Uganda. But I didn't use what they used here. I used the bevel gears up there. But the students, given this assignment, they optimized it using the simple chain. Finally, in conclusion, there we are. Arts and humanities.
Perfect timing. We've got a few minutes for questions.
Was the challenge the students being able to use spreadsheets, or was the challenge the students being able to solve human problems?
No, the challenge, originally, the
What did they
challenge,
have the most problem with? That's what I'm saying.
well,
The students.
After doing this,
No, before. In other
oh
words,
no, before the issue was the iterative nature of design.
That's it.
Yes, because first of all, they couldn't optimize.
Yes.
Secondly, they couldn't integrate.
Got it. Okay.
Okay?
So the spreadsheets wasn't a problem, it's just a tool.
No, the spreadsheet was a tool, but which aided integration of all these things, and therefore made the whole calculation work easier.
Did you consider using something like SMAT Studio rather than Excel? Because SMAT Studio shows the equations as they are calculated. Excel, I always find that cumbersome.
I didn't have time to show you, but the equations are embedded. The spreadsheets are specifically designed by me for the students. So the equations are there. Okay?
Oh, okay.
The equations are there on the spreadsheet. And Excel, of course, being what it is.
No, but that's what I was asking, you see. Because there's a lot of spreadsheet work then, I was wondering.
I would suggest that you have a look at SMAT Studio as an alternative. I think it could be more effective than Excel.
Yes, that's okay. That's fine.
Is that a free package?
It's free. There's MathCAD is the commercialized one, but SMAT Studio is a free package, and it's the nice thing about it. You write your equations and they lie. If you give values to them, they calculate it as you go along, and it keeps units as well. It checks units for you.
No, here I think I beg to refer on that one, mainly because